Okay, so this is lesson 6.6, where our objective is to model real-world data using sine functions. Technically listed as sine and cosine functions. However, I will be talking about music harmony, where we only use sine functions. So if we can recall, in trigonometry, this is a sine wave. So if we have sine of x, we'll have our graph, and we'll have waves that look a little bit like this. We can use these same fundamental techniques we use to graph sine waves in order to demonstrate musical harmony between many notes. And we can also find their dissonance, which is when you just, slam on a bunch of keys on a piano and it sounds awful. That's what you're doing, you're creating dissonance. Let's just try one for now. Note A. It has a frequency of 440 hertz. Which, if you didn't know, hertz is just how many waves pass through your ear per second. To solve this, we need to write a sine function to represent A, which would be y equals sine 880 pi t. And you can just plug these into Wolfram alpha, as Mr. Arthur would have showed you previously, and then you can find your graphs for that. So we can look at harmonic demonstration with our D chord, which consists of A, F sharp, and D. This does get kind of tedious at first. We need to define our period when we start with D. So we will get D with a frequency of, really big frequency actually, middle D, 291.665 hertz, which means D just cycles through your 263.665 times a second. So to get a cleaner graph, we need to make our function y equals sine 292, I believe, yes, 294. Pi times t. To define our period, we don't want to go on forever, so we will just use our basic unit circle, 1 of 2 pi. So then our function will look like y equals sine 2 pi 294 times x. So to make our lives easier, we need to go 2 pi on top here over 2 pi times this number, which is a 3. And multiply that by 1 over this number. You can put your calculators away because I have solved this previously. 0.034 seconds will be our period here. So now we have to graph this bad boy, which, because it has a high hertz, you'll have a lot of waves there due to its also high amplitude, which just means that you have a higher pitch there. So your sine wave will kind of look something like this for D. We have to do this 2 more times. It does get a little tedious, but however, the results are pretty rewarding. This time we'll do F sharp, which is a lot more of our friend as it stands at a much cleaner number at 370 hertz. So F sharp would be y equals sine 370, excuse me, 2 pi times 370x. Our period to define it will be 1 over 370. And our graph, because it is a much lower pitch, will look a little bit different. It'll start from the same point, but it'll be a little bit more like this. And I should probably make that a different color. Again, very tedious task, but we will go back to A, which is at 440 hertz. Again, function and period. A is 2 pi times 440 t, or x, whichever one you prefer to use. And our period is again 1 over 440. And that graph is also much cleaner. If we stand, it looks a little bit like this. Ta-da. So if I was like the great artist Pablo Picasso, you could probably see my harmony better on these graphs. But if you plug them in, you could also see them much better than just my drawing. But as you can see, they come together at about, I'd say, 0.007. And they all come together right here. That would be about 0.014. And that's how you get harmony in music. They're consonant. The D chord does end up being consonant, because they do link up like two cool kids on prom night at those points. So you can find dissonance with 2 or 3 other notes that don't quite have that. However, we're not going to do that right now, as we're just modeling music harmony with sine waves. But you probably might say, Professor Montoya, you're using chords. Of course they're consonant. However, follow me, Gabby, please. You see here on the standardized piano, I'm going to play something that is not with chords, when the great Aubrey Graham and Jack Webster, or as you may know them, Travis Scott and Drake, created their great Grammy-nominated composition of Sicko Mode. They also use this principle. You have G, separated by a whole step and a half step, B flat, and then another whole step and a half step at D to make perfect intervals and create, which sounds a lot better than, that was dissonance, and with this, and then creating it again with their other segment of the intro, F, A, and D. So this is used all over in the real world, and math and music are everywhere. When they intertwine, you may think the fun is sucked out of them. However, your results will never, ever be disappointing. Thank you. This was 6.6 Music Harmony.